Hey, test delay, everybody, test delay. So, today we're going to take up the second chapter in class 11 chemistry, and that is structure of atom. Now, in today's lesson or video lesson, you're going to learn about discovery of these subatomic particles. Namely electrons, protons, and then neutrons. Now you remember studying about something called the atomic theory proposed by Dalton. We call it the Dalton's atomic theory sometime back in 1808. So in that theory, you remember studying about Dalton saying that an atom is the smallest particle of an element which is indivisible. But after that, later on, I should say, other scientists, in fact, they came to know that an atom is not indivisible as such, because an atom consists of subatomic particles. So that's what we're going to learn about in today's lesson. Now, in fact, we know that there is a rich diversity of chemical behavior in the atoms of different elements, or different elements, they have different chemical behavior, and all that is because of the differences in the internal structure of their atoms. That's it. So now, to begin with, we're going to start with the discovery of electrons first. So it was sometime back in 1850 that Michael Faraday, he did these experiments and then came up with the discovery of what are today known as electrons. Now, in his experiment, Michael Faraday, instead of use this device, here it's called the cathode ray discharge tube. So he did his experiment using this cathode ray tube. It's called the cathode ray discharge tube. And here, as far as the cathode ray discharge tube is concerned, it is actually made of glass, and it is fitted with two thin metals at the two ends, which form the electrodes. And then the electrodes, in fact, one terminal is connected to the one electrode that is connected to the negative terminal of the battery, that becomes the cathode. Then the metal plate or the electrode which is connected to the positive terminal of the battery is the anode. And now it is said that this electrical discharge is observed only at very high voltage and very low pressure. See, a gas is taken in this discharge tube here, and the gas inside is at a very low pressure. The pressure can be reduced by evacuation with the help of this outlet here. It is connected to a vacuum pump. So with the help of the vacuum pump, the pressure inside the tube can be reduced. So the gas inside the tube is at a very low pressure, and then a very high voltage of electricity is applied. So this electrical discharge is observed in the tube only at very low pressure and high voltage. Right? That's it. And now, when a sufficiently high voltage of electricity is applied through the tube, this electrical discharge is observed. So the electrical discharge is observed only when a high voltage of electricity is applied through the tube. The flow of the current here, that is from the cathode to the anode, is because of the stream of particles moving from the cathode towards the anode. So here there is this flow of current through the tube, that is from the cathode towards the anode. It's because of the flow of a stream of particles, and they seem to be moving from the cathode towards the anode, and that's the reason why these particles, they are called as cathode rays. Now these cathode rays, they are not sort of visible as such. They can be made visible with the help of some fluorescent or phosphorescent material like zinc sulfide. So now, to check the flow of these particles from the cathode towards the anode, they did a second type of experiment in which, this is shown here. You will see that the anode here has some holes in it, and then the portion of the tube behind the anode is coated with a fluorescent material like zinc sulfide. This is the fluorescent screen here, and once again when the set is switched on with a gas in it at a very low pressure and a very high voltage of electricity here, they start seeing these small sparks or flashes of light here just behind the anode, that is on the tube here, right behind the anode. So that's because when these charged particles, they started moving from the cathode towards the anode, some of these particles, they passed through the holes and then they hit or they struck the sort of a portion of the tube behind the anode here, and it started giving sparks or flashes of light there. So this indicated that there were these particles coming from the anode and then moving towards the cathode, and these particles were called as cathode rays, right? So this is all about how cathode rays were discovered. And now, based on these experiments, that is based on the results obtained from these experiments, you can see that the following properties of cathode rays were established. Like the very first property that you can see here is this. That is, the cathode rays, they start from the cathode and move towards the anode. So the cathode rays, they always start from the cathode and move towards the anode. The second one is that these rays are not visible as such. They can be detected by fluorescent materials like zinc sulfide, for instance. Now these fluorescent materials, they glow when they're struck at these cathode rays. So as I explained here. And then the third property here is cathode rays travel in straight lines. So these cathode rays, they always travel in straight lines like light in the absence of electrical or magnetic fields. So when there is no electrical or magnetic field applied, then in fact these cathode rays, they always travel in straight lines. The fourth property here is, in the presence of electrical or magnetic field, the behavior of these cathode rays is similar to that expected from negatively charged particles, suggesting that the cathode rays consist of negatively charged particles called electrons. So here, when they studied the behavior of these, cathode rays, they found that these cathode rays, they behaved very much like other negatively charged particles. So this gave a suggestion that these cathode rays consist of negatively charged particles called electrons. So these cathode rays are actually nothing but electrons. That's it. And then the next property, the fifth property, is the characteristics or properties of cathode rays. They do not depend on the material of the electrode used or the nature of the gas present in the tube. So these categories are nothing but electrons. So like the properties of these categories electrons, they did not depend on the material of the electrode used or the nature of the gas present in the tube. And the last thing is categories are made up of material particles, and this fact was in fact shown by the fact that when a light paddle wheel mounted on an axle is placed in the path of these categories, they started moving. So this shows or proves that these category particles are nothing but, these categories, they are made of material particles, they are particles. So this is all about the discovery of electrons and the properties or the characteristics of these categories, that were established based on these experiments. So next, we are now going to move on to something very interesting and also something very important, and that is the charge to mass ratio of an electron. It is denoted by E by ME. Now, this experiment was in fact done by J.J. Thomson sometime back in 1897. So now, in this experiment, you will see that J.J. Thomson made use of the cathode tube, and here he's sort of applied these two fields, that is electrical field and magnetic field. So these two fields, in fact, they are applied at perpendicular to each other, and also to the flow of, that is to the direction of flow of the particles, that is your categories or electrons. Now, based on this experiment, he in fact found this charge to mass ratio. Now the interesting thing here is, when no electrical field or magnetic field is applied, these categories or these electrons, now they travel in a straight line, and they are seen striking the fluorescent screen here at this point B, that is in the absence of an electric field or a magnetic field. So this is supposed to be your an electric field. You have the positive terminal of the plate here, that is the positive plate here, positive electrode, then the negative thing here, and the magnetic field is again, this is the one here. You have this magnet with the north pole that side and the south pole this side. Now, so as I suggest, now in the absence of either the electrical or the magnetic field, the categories of these particles, they travel in a straight line, and they struck the fluorescent screen here at point B. Now, in the presence of the electrical field, what happened is, these categories or these particles or your electrons here, they are seen moving upwards, and they strike the fluorescent screen here at point A. And then again, in the presence of this magnetic field alone, without the electrical field, the categories here, they seem to get reflected downwards, and then they are seen to strike the fluorescent screen at the point C. This is what was observed. And then, in fact, he applied these two fields simultaneously, and then did a lot of studies, and he was also able to adjust the strengths of the electrical field and the magnetic field in such a way that he would make the categories or these particles come back to the original path and strike the fluorescent screen at this point B. So these are some of the interesting things that J.J. Thomson did in this experiment. And the final thing is that he found the charge to mass ratio of an electron. Let's talk about this just a minute later. Now, see, as far as the deflection or the deviation of these particles is concerned, it is found that the amount of deviation of the particles, that is your electrons here or categories, Now, from their path or original path, in the presence of electrical or magnetic field, that is the amount of deviation of these particles, in the presence of either an electric field or a magnetic field or both, they depend upon the first one, the magnitude of the negative charge on the particle. So the deviation of these particles from their original path in the presence of an electrical or magnetic field depends upon, the first thing is the magnitude of the negative charge on the particle. So it is saying that the greater the negative charge on the particle, the greater is the deflection or the deviation of these particles from their original path. And the next thing that it depended on was the mass of the particle. Now here, as far as the mass of the particle is concerned, the lighter the mass of the particle, again, the greater is the deflection or deviation of these particles from their original path. And then the third point it depended on was the strength of the electrical or magnetic field. And here it is found that the greater the strength of the electrical or the magnetic field, the greater is the deflection or the deviation of these particles or your electrons from their original path. That's it. And now, based on these things that it did here in this experiment, see, it is said that by carrying out accurate measurements of the amount of deflections of the particles, that is the electrons, due to the electrical or magnetic field, J.J. Thomson was able to determine the value of E by ME, that is charge to mass ratio of an electron, that is E by ME is equal to, he found this value, that is 1.758820 into 10 raised to the power 11 coulombs per kg. So this is in fact a very important value here. That is the charge to mass ratio of an electron. So here this E is the magnitude of the charge on the electron, and ME here is the mass of the electron. So during J.J. Thomson's time, the actual charge on an electron was not known, and also the mass of an electron was not known. Now let us see something very important and very interesting happened after that. That is the it is the charge on the electron. So you're going to see who actually discovered this thing called the charge on the electron. So the next thing that we're going to take up is the charge on the electron. Now, in fact, it was discovered by a scientist named R.A. Millikan. So Millikan was a scientist who discovered who found the charge on an electron. So I put it this way: charge on the electron. Charge on the electron. Now, this was some time back in 1909. It was in the beginning of the 20th century, I should say. So it was by a scientist named R.A. Millikan. Millikan, right? All right. And now here, this scientist by name Millikan is said to have done an experiment called the oil drop experiment, and in this experiment, he managed to find the charge on an electron. So here, the charge on an electron was found to be charge on an electron. I should say the electron rod. It's called oil drop experiment. Charge on an electron is equal to minus 1.6 into 10 raised to power negative 19 coulombs. This was what Millikan actually found based on its oil drop experiment. The experiment is called the oil drop experiment. Now this is an experiment that's a little bit hard to understand. A brief explanation of this oil drop experiment is given in a textbook. You can go through that. And now, after Millikan found the charge on an electron, that is minus 1.6 into 10 to the negative 19 coulombs, right? Then J.J. Thomson had found the ratio of charge to mass of an electron. You already have this result here. And then by combining these results, you know, they found the mass of an electron. And in fact, today the accepted value of the charge on an electron is something like minus, or that is expected, or the accepted value of charge on an electron is minus 1.6022 into, to be more precise, is a negative 19 coulombs. This is the accepted value, right? Not if I'm not wrong. All right. So now, combining these results, we know that E by ME is equal to, it's 1.758820 into 10 raised to the power 11, that is coulombs per kg. And now here we see that the charge on an electron as found by Millikan is this one. It's taken as 1.6022 into 10 raised to the power negative 19 divided by, this is the mass of the electron, is equal to 1.758820 into 10 raised to the power 11. Now when we simplify this expression, that is, the only unknown quantity here is Me, that's the mass of the electron. It is given by, when you cross multiply, what you're going to do is, you have to divide this number. That is 1.6022 into 10 raised to the power negative 19 by, it is 1.758820 into 10 raised to the power 11. We take it in top, so finally, on simplification, the value here happens to be, I've got this 9.1094 into 10 raised to the power 31. It is negative 31 kgs, right? Negative 31 in terms of kilograms. This is. So this is finally the mass of an electron. It is 9.1094 in terms of negative 31 kilograms. So now the very interesting things that have happened are like, they found the charge on an electron, and then they also found the mass of an electron. So this is all about the charge on an electron, based on which we found the mass of an electron. Now the next thing is we're going to move on to the discovery of protons. So discovery protons. Now in the discovery protons, what is done is the cathode ray discharge tube was modified, and using this modified cathode ray discharge tube, then they sort of discovered the protons. Now protons, they are positively charged particles. So let's just see how these protons were discovered. So as far as the discovery of protons is concerned, let's see, we write discovery of protons and neutrons together, right? So as I said just now, in the discovery of protons, they used what is known as a modified cathode ray tube. So with the help of this modified cathode ray tube, they managed to discover protons, and it was actually discovered by Goldstein, scientist by name Goldstein, sometime back in 1886. So this electrical discharge now carried out in a modified cathode ray tube led to the discovery of electrons. Now, the interesting thing here is with regard to the cathode here. Here, in the tube, in fact, you have the electrodes, that is the cathode and the anode, and here the, anode, sorry, not anode, I mean the cathode had a hole in it. It was a perforated cathode that was used, and then these positively charged particles, they passed through this hole in the cathode. And that is why these positively charged particles are also called as Catenary rays or anode rays. Now, the next thing is that we are going to learn about the characteristics or the properties of these positively charged particles, or Catenary rays or anode rays as they call. So, we'll take on. Alright, the characteristics of these. Now, positively charged particles. Positively charged particles. Now, the characteristics of these positively charged particles are very similar to that of your cathode rays. The first thing is, you know that they are, now these positively charged particles, they are not produced or emitted from the anode as such, but they are obtained by knocking out the electrons present on these gaseous atoms. So the first thing is, they are, you should know that they are produced by knocking out electrons from the gaseous atoms. Now these gaseous atoms, in fact, they are present in the cathode ray discharge tube. Gaseous atoms present in the space between the cathode and the anode. Cathode and the anode. So you should know that they are not emitted by the anodes. They are not emitted by the anode. This is what you're supposed to know. They're simply positive charge, so they are, or these are, right? These are simply positively charged gaseous ions. Positively charged, these are simply positively charged gaseous ions. Gaseous ions, right? Maybe H plus or He2 plus or whatever. The second one is, now these they travel in straight lines, just like your cathode rays. They travel in straight lines. All right. So these positively charged particles, they travel in straight lines, and then the most important thing here is the charge to mass ratio. The charge to mass ratio of these particles. is found to depend on the gas from which they originate. Depend on the gas from which they originate. So, like in the case of your cathode rays, you see that the charge to mass ratio is always the same, irrespective of the gas taken in the cathode ray tube. You may take hydrogen or you may take helium or some of the gas. It's because the electrons, that originate from the cathode. So it's only the electron that is considered charge of the electron divided by the mass of the electron in the case of cathode rays. So it is always fixed, it remains the same. The ratio you're seeing, E by Ma in the case of electrons, right? Cathode ray, there is 1.75 W20 into 10 raised to power 11 coulombs per kg, that is fixed. But as far as your positively charged particles here, protons are concerned, the charge to mass ratio, that is charge on a proton divided by the mass of what do you call positively charged gaseous ion. It is different for different gases. That's it. This is what it means. And the next point is now some positively charged particles carry. So these particles carry a multiple of the fundamental unit of electrical charge. Multiple of the fundamental unit of electrical charge. So the charge on these positively charged particles, it is not the same, it varies. Sometimes it is a multiple of the fundamental unit of electrical charge, in the sense like it is 2 times the fundamental unit of electrical charge in the case of some gases. In some cases it is 3 times that fundamental electrical charge, and so on. Now the fifth one is the behavior of these particles is opposite. Okay, so the behavior of these particles in electrical or magnetic field is opposite to that of opposite to that observed in cathode rays. So these are some of the characteristics or properties of these positively charged particles. So the first thing is they are produced by knocking out electrons from the gaseous atoms present in the space between the cathode and the anode, that is in the cathode discharge tube. Then they are not emitted by the anode. These are simply positively charged gaseous ions. So these positively charged particles, they are nothing but gaseous ions obtained from the gas taken in the tube. And then it is said that these positively charged particles or anode rays or canal rays, there is nothing but your protons, right? Protons in the sense, in the case of hydrogen, it is the proton, right? They travel in straight lines. And then the charge to mass ratio of these particles is found to depend on the gas from which they originate. It is not the same for different gases, that's one thing. Then some positively charged particles carry a multiple of the fundamental unit of electrical charge. And then the last thing is the behavior of these particles in electrical or magnetic field is opposite to that observed in cathode rays. Now these are positively charged particles, and then the others, that is in the case of cathode rays, they are negatively charged. Cathode rays is nothing but your electrons, and these positively charged particles or your canal rays, they are nothing but your positively charged gaseous ions, maybe H plus or Ha2 plus, or depending on the gas that is taken in the discharge tube. Now the next thing is we're going to take up the discovery of now neutrons. Discovery of neutrons. Now neutrons were discovered by the scientist named Chadwick, and it was sometime back in 1932, to be precise, sometime back in 1932. Now after the discovery of electrons, Then after the discovery of the protons, scientists, in fact, they felt the need for the presence of some other electrically neutral particle in an atom in order to account for the overall mass of an atom, because they're not satisfied. They felt that there must be some other neutral charge which must be present in an atom to account for the overall mass of an atom, because when they considered only the mass of the electrons and the protons, it was not matching matching with the overall mass of the atom. So they very much felt the need for the existence of some other neutrally charged particle in an atom. And these neutrally charged particles, they were discovered by the scientist named Chadwick sometime in 1932. And here, now what is done is, it is said that, here, he instead of bombarded these, thin sheets of beryllium with very fast or high-speed alpha particles. So when these, when a thin sheet of beryllium was bombarded with alpha particles, then he found that these neutrally charged particles, particles having no charge, were sort of emitted from the beryllium sheet, and he called these particles as neutrons. So this is about the discovery of neutrons, and these neutrons, they were found to have a mass slightly greater than that of proton. So finally they came to the conclusion that apart from electrons and protons, and there are also these particles called neutrons that are present in an atom, and then finally they could account for the overall mass of an atom. So the overall mass of an atom actually includes the mass of the protons, the mass of the neutrons, and also the mass of the electrons. So this is all about the discovery of neutrons here. Now the next thing is with regard to the properties of these fundamental particles. Like I'll just write, these are some important properties. The particle here, right? And then next you have the symbol for the particle. The symbol is here, and then you have absolute charge on the particle. Absolute charge, that is the actual charge that is there on a particle, and then you have the relative charge on this particle, and then you have mass, that is mass in kg, and then this is the longest one, then mass, that is AMU, right, or unified mass, and then finally it is the approximate mass. We take approximate mass, AMU, right, approximate mass, and that is unified mass. Just a minute. So these fundamental particles, the first one we're going to talk about is the electron. It is the electron, and then next we'll take up the proton, and then the neutron, right, and finally the neutron. These are the three subatomic particles. The unit here is E. The symbol here is E, proton P, and then neutron N. Absolute charge on electron, it is now minus 1.6022 into 10 raised to the power negative 19. This is in terms of coulombs, right? Alright, and then for a proton, it is positive 1.6022 into 10 raised to the power negative 19 coulombs. If I'm not wrong, this is charge on a neutron is 0. Now the relative charge on an electron is taken to be minus 1, that of proton plus 1, and neutron it is 0. And now the next thing is mass in terms of, that is in kilograms. Mass, first let's write the mass of a proton. In terms of kilograms, the mass of proton is 1. We remember writing something as 267 into 10 raised to power negative 27, right? Negative 27 kg. And that of a neutron is slightly more than that, 1.67493. 493 into 10 raised power negative 27 kilograms, and that of an electron. Now the mass of an electron is, as we found out just now, the value there is 9.10939 into 10 raised to the power negative, it is 31 kg. So this is an extremely small number, because here this is 9.10939 into 10 for negative 31 here, whereas this is negative 27. So we see that the electron has the smallest mass here, and next it is the neutron, and finally the lightest of all these is the lightest is electron, and then the heaviest, I should say, it is the neutron, and then next it is proton, and the lightest is the electron there. Okay, that's it. And then mass in terms of atomic mass unit or unified mass, for a proton it is 1.00727. For a neutron, it is a little more than this. It is 1.00867, and that of an electron, it is 0.00030 and then 54. So this is much smaller than these two. So this is in terms of atomic mass unit, comparing it with 1/12 the mass of an atom of carbon-12, right? That's it. And then the approximate mass, that is in atomic mass unit, this is the mass of an electron is taken to be 0, and that of a proton is taken as 1, and that of a neutron is also taken as 1. So these are the important characteristics or properties of these subatomic particles, that is electrons, protons and neutrons. So this is all about the discovery of protons and neutrons. So with this, we have now come to the end of the discovery of these fundamental particles, or the subatomic particles, namely electrons, protons and neutrons.